Hi folks, John McIntyre here, bringing you a video on a cool feature I've been working on in Unreal Engine to generate procedural terrain. It's all done through blueprints, and you can see the result here. Basically it takes a whole number of pre-made building blocks based on hexagonal tiles and places them on a hex grid. It then rotates them so they face the correct direction, ensuring consistency between raised and non-raised edges, and I can control the density across the whole field, allowing control over where the raised sections occur. Here you can see the effect from very simple template hex tiles, but these can be developed to produce prettier results. So the idea is to have higher detail tiles that match seamlessly at the interfaces. These could then also be cliff edges or ramps or stairs, which would allow the player to traverse between raised and lowered sections. Additionally, tiles could have caves and tunnels for added traversal opportunities. It's also possible to do multiple layers, so to stack strata on top of one another. And I'm building all of these elements into the additional features for this tool. The whole thing is built as follows. The first step is to generate the field, and this is done by applying either 1 or 0 to each edge of the tile. 1 means it's a raised edge, and 0 means nothing or gap. So a tile with zeros all around the edge equates to a completely base level tile, while 1s all around the edge equates to a completely elevated tile. To create interesting terrain, obviously we want a random spread of 1s and 0s to get variation. The next step is to make sure the field is consistent, so this means looping through the field again, this time making sure all the edges match with their neighbours, and once the field is consistent, then we can start selecting tile shapes to place on the field. So I've created a number of default tile types with raised edges ranging from 1 to 6. There are multiple types for the more complex tiles, like those with edge numbers between 2 and 4, because obviously the combination of ordering of raised to non-raised edges creates a number of different patterns. I do a filtering step where I select only the tiles with the correct total number of edges. So for instance, if there are only 2 1s around the whole loop of 6 edges, then I will only select those tiles that have a sum total of 2. Where those edges fall is not relevant at this point. But having selected a number of potential candidates, I then go down to the actual business of fitting them into the field. As an example, using this simple 2-edged piece, we can see that although the shape is correct, it needs to be rotated to fit the field. I do this doing a bit string rotation and comparison to check whether the tile fits, and numerically it looks a little like the equation in the bottom right of the screen. The top bit string is for the piece I've selected to test, and the bottom is for the tile field I generated at the start. In the default position they don't match, but shifting the bits to the right with the 0 at the end wrapping around to the beginning, like so, makes them equal, meaning we found a match. So if I go into function shell and I have a look at this function I've got here, this is the event that governs the creation of the field. It's called create field. You can see in this lower left hand corner here of the details panel I've got call and editor checked, so that lets me drive it in the editor. It's got the sequence, 4 main branches coming off the sequence. The first one is just some housekeeping. You can see here the comments housekeeping. I look for all previously generated hex tiles, so get all actors of class hex tile, loop through that array and then destroy the actors. And once I've cleaned up, I can then go and start creating the new field. So if we look at the branch that's coming off then 1, if we go right to the end of it, it's really only doing one thing, and that is it takes this map of 3 int and bit array, and it just adds a new element to it. Now this map is quite literally our field. So this each you can see I've called it tiles. It is a map of all the tiles in the field. The key value, or sorry, the key of the map key is this struct called 3int. So if I go over to 3int, you can see here it's just 3 integers, red, green and blue, hence RGB. And then the value, the map value, is a bit array, and if I go to bit array, it's really simple. It's just an array, a Boolean array, as you can see here. So this is in principle generating the field. So I need two things. I need to generate these three coordinates, the RGB, and then I need to generate the actual edges. So we have two loops, a red loop and a green loop. They run from 0 to the top end number, and the top end number is set here as this literal of 14. This effectively sets the radius of this projection method. So it'll create 14 tiles across, up and down. So basically it'll be 7 tiles from the center to any edge. So I say 7 because obviously I divide this value by 2, and then I subtract the index from each loop by that 7. So I have a red loop, a green loop. They just become the R and G coordinates. In this method, which I won't go into too much detail, there is actually an identity which says that the sum of all three should always equal 0. So that automatically gives you the identity for blue. You can see here blue is just set to the sum of R and G multiplied by -1. And then I have a check here which just caps the radius. So this is just a radius cap. And this basically says, look at the absolute value of each coordinate, add them all together, and check that they are less than your intended radius here of 14. And if that's true, obviously then it goes through and adds this element to the map, and just setting those coordinates as we've created them there. So how do we set the value? Well, the value is set down here. You can see here we've got our make array into our make bit array struct, and I break out all the individual values in that array. Obviously there need to be 6 elements, so 0 to 5. I have 3 variables of note. Here at the bottom I have a global density. This lets me essentially have a factor that controls the total density across the whole field. But I also have some local density factors. I've got internal and external. I use the radius of the field again to linearly interpolate between these two values, and then I take whatever the interpolated value is and multiply by the global density. This gives me a factor somewhere between 0 and 1, and then I check that that is greater than a random float in the range of 0 to 1. And then I set that to the edges. Now obviously in this case, if I have very high numbers for the density, so if the density is 1, I will always generate a raised edge. If the density is 0, I will always generate a non-raised edge. And obviously we want some interesting terrain, so we want a value somewhere in between that. Having the local density control, I like doing this because it means you can have a sort of a gradient from the center of the field to the outside of the field, so you can sort of create either a sort of an enclosed ring, or you can sort of have a sort of a mountain, a mountainous region that sort of spikes up in the middle. So I just repeat that for each element in the array, turn that into the bit array, and then that forms the map value of the tile. Next in the sequence, what I do is do the tile consistency. So making sure that each of the tiles matches its neighbors. So I take my tile map, break out the keys, shuffle that array, and then loop through that array. And for each element, I plug that element into the get tile neighbor masks function, which is a subfunction that I've created. So if we go into that, it looks a bit complicated, but really it's just one simple procedure repeated 6 times. And just broadly speaking, if you can see here, the very last node in this sequence is the return. So I've just put it up here just for visibility. we're returning the slots. So essentially what we're doing is looking at all the neighbors and returning the edges of those neighbors with respect to the tile. So that tile is called origin here. We break out the RGB coordinate, and this is another reason why I really like this method of storing the unprojected 3D RGB values, because it's really simple, or it's really convenient to find the neighbors. So all we really need to do for this is to increment each one of the neighbors. And if you remember back, I said there's an identity that says that the sum of RG and B always have to equal 0. Well, if we increment one neighbor, then we obviously have to subtract from one of the others. And this is exactly how we find all the neighbors. So if you add up all the possible combinations, you get 6, and unsurprisingly, a hex tile has 6 neighbors. So going through the first one, we have red, green, and blue. I just add 1 to R and subtract 1 from G. Blue stays the same. I look for that key in my map and then get the value of its edges. And of course I'm the 0 edge, so I will be next to edge number 4. And so that's why I get element number 3 from my neighbors array. I then set that to my return array as that value, and if not, then I just set it to 0. So that's what the other side of this branch statement is, just setting it to 0. But making sure you can see here the index. So this is index 0. Its neighbor is obviously 3 from the neighbor. And then if we step through the sequence node, you can just see I'm just going through all the different combinations. So in the next one, I keep R the same, but actually I subtract from G and add 1 to B. And then I get I get element number 4 from that neighbor, and then set my index 1 to that value. And it goes all the way through, so you can see, so I go through setting my own 0 to 5, and then of course I'm getting the neighbors obviously from 3 to 5, and then it wraps around back to 0, 1, and then 2 there from the neighbors. And that's it. So it is a little bit spaghetti code here, but yeah, just a very, very simple repeated process. Having got that bit array, I basically just overwrite the value of the tile. So I do lose some of the generation generation work I did earlier, but effectively this is how I ensure that all the tiles are equal to each other. So the last step in the sequence, if we come to the loop, follow it down here, the sequence, we again get the tiles, get the keys, we do another loop through all the keys, we use those key values to find the bit array from the tile that we are currently looping through, and we break out the edges and we get the number of edges. So again, another sum function. This is very simple. If we look at this, it just takes the loop of those arrays and it adds the value to a byte variable and then returns whatever the sum of that is. So if there are 2 edges, it'll return 2. If there are no edges, it'll return nothing, and of course 6 edges return 6. So that's very, very simple. It'll just return the number of edges as it says on the tin, and then it passes it to this function which says get possible tile fits. So this is our pre-filter. So again, not going to go into too much detail. When I store the different tiles in my data table, I store how many edges they actually have in total, and this just looks for that value and says if they're equal, then return that row name. So that's what those options are. It loops through each of those options. Again, for each option, it finds that entry in the data table, and then breaks out the data table row. So each row in the data table has a mesh, has a byte mask and it has a sum associated with it. So previously I was filtering on the sum. Now I'm actually interested in the bit mask, and I do this bitwise equals between that array and the array that I've broken out from my tiles map. So this is where the real action happens in this bitwise equals. So if we go into that, so I've got my two arrays, A and B. This is where I'm comparing the two bit strings together. The first is my rotation. So this is the rotational offset here. This is what's happening in this first loop, and you can see the first thing I do once I've gone into that loop, and I'm essentially looping between 0 and the last index, so I want to loop through all the values in the array, is I set this return offset value, which is a local variable. So that essentially records the loop number of the outer loop, or the counter of the outer loop, and then it goes into the inner loop, and the inner loop just is doing the check between all the values. So what do? Well, I get again my first array. I then get the value from, so I get the value from array A, and that just directly goes into the index. That's what this get here is. But then I have another get, which is the comparison array, which is B, and that I basically have to add the offset to. So I add the offset, and then I also do this modular function, which essentially provides the wrapping. So this provides the index wrap for the array, and then I check whether they're equals, and if they are equal, then I check success, and then just let the loop continue. If they fail, however, I know that obviously I don't have a match, so I don't need to do any more comparisons, and that's why I drive this break. When it gets to the end of that loop, it then checks whether it has success. If it does have success, then it'll break the outer loop, because basically we've found the rotation, or we found a rotation that works, and so that's the rotation that we plug into that we want to return. So there's no point doing any more calculations. We just break the outer offset loop, and then we return both success and return offset. Of course, if you go through and you never find a match, this loop should break up fairly quickly as soon as success, or as soon as it's unsuccessful. Essentially gets to the end of this loop, it tries a few more, and they all fail. Eventually what will happen is the offset loop will run its course, and then it'll get to the end, and the function will basically say, no, well, it wasn't a match. In that case, we go back to our function shell here. If it wasn't a match, then obviously we'll just look at the next row. So we'll just look at the next possible tile that we have in our table of tiles. But obviously if it's successful, then we create a new hex tile, and after creating the hex tile, we then we essentially break that loop of possible rows to check in the data table. So we create a hex tile with a particular transform. Here's where the projection of the coordinates happens. So of course I make the transform here. The yaw, so this is the z-axis rotation, is whatever the offset is times 60, because obviously however many times, if you're rotating once it's 60 degrees, twice it's 120, basically just you're rotating by the degrees in the hexagon. The location is set by these two colorful comments here. So I get my R, my 3int structure here. The x value is g cos 30 minus b cos 30. and the Y value is basically R, and then it's we take the sum of G and B cos 30 and we add those together, and then we subtract that from R. So that gives me my X and Y coordinate. Z is basically just constant 0, so when I do multiple layers, this will obviously be where you then control where the Z height goes in. And then I multiply it by the tile size. So the tile size in this case is deliberately been kept rather simple, so they are just the separation is 1,000 unreal units. So I multiply those coordinates by 1,000 unreal units, and that gives me the location for where I spawn the tiles. And that is basically it.